Hello, welcome to episode 33. I've got a lot of requests to go through this question. So, if you watch my previous episode, it's just the question before. So, well, it's question 13 anyway. So, that's the January 2023. Okay. Um, Look at this. 8 marks. Oh, so sorry. It's not even 8 marks. It's 9 marks. This is the end of section B. So, um, well, once again, work backwards. Okay. So if you look at the formula sheets, you will find that the modulus of rigidity, the G, is the shear stress over shear strain. So G is equal to shear stress, which is the tau, and over uh, uh, look like a what? Well, I think it's a gamma. Um, so that's shear stress, and this is shear strain. Okay. So what we need to find is to find shear stress and shear strain one by one. So what we'll do is I'll start off with shear strain. So shear strain is equal to delta L over L. So this delta L, now if you have written tau already, you will know it's F over A. So therefore it can't be this for F. It's got to be to do with those, yeah. So that means delta L must to do with some change, and so you can see there's a change of movement from the original position. So I would say the delta L must be 1.5 over divide by, well, to move it to the left, or if you like, or to the right, it's all related to how long this rivet is going to be. The longer it is, the easier it's probably going to uh, twist like this. Okay, so L in this case is the length here. Okay, so this is the length originally there. Okay, so it's actually 20. So that's 10 and a 10. Okay. Okay, so, and they are in millimeter. So if you divide by the millimeter by millimeter, you should get the same answer if you have got convert them into meters. So I won't bother with that. But anyway, millimeter and millimeter cancel out anyway, so it becomes unitless, and so it's 0.075. Okay, so we got this now. So now we need to work out the tau F over A. Now, just so that you know, if I was to pull this bar to the left, this can't possibly do that if I not sort of fix this part onto some sort of rigid position or amount. Okay, because if you don't mount this part somewhere, what this will only going to do is just going to pull the whole thing to the left hand side, isn't it? Yeah, think about that. So therefore, this force here is going to equal to this because it's the reaction force. Okay, so when you deal with the force, you only really need to deal with 250 kilonewton, not 2 times 250 kilonewton. Okay, so you can actually fix, say you want to fix this part and then pull that side. What would happen is the rivet would have change, the delta L would have been on this side instead. Yeah. So tau, before we find tau, let's find area first. Area is obviously to do with how uh, how wide the pin's gonna be. So it's not gonna be um, uh, the area of the cross section. Okay, so as I say, what I mean by that is it's not the area of this. Okay, So it's the area of the cross section of the cylinder, which is the pin here. Okay, this area here. Okay, so let me just tidy this up. So it's this area we are talking about. Okay, which is a circle. And so A is equal to pi r squared, but in engineering, we like to use diameter. So it's pi d squared over 4. Okay, so since the diameter is given to us and is 14, so therefore is pi multiplied by 14 square over 4. And the area is equal to 153.93 millimeters square. So therefore tau, which is the shear stress, is equal to 153.93 millimeters square divide, sorry, go back to that. Is force, yeah, so it's 250,000 Newton divide by, now be careful here, we need to convert the millimeters square into meter square. Now I think I've done enough now. Hopefully you should be an expert in this. Is not to divide by 1,000, is to divide by 1,000 square. Okay, because it's a area scale factor, so you have to divide by 1,000, which is the linear scale factor, and then square the linear scale factor, which is the area scale factor. Okay, so that's they basically divide by 1 million. Okay, and you will find that your calculator, if you are in standard form mode, then you would have 153.9 times 10 to the power minus 6, or alternatively is 0.000015393, 3 noughts, yeah, after the decimal point. And that would equal to 1,624 Newton meters square per meter square. That's the units for the tau. Why do I know that? Because that's newtons, that's meters square, so it's Newton per meter square. But tau is also measured in Pascal because it's stress, so it's got to be pressure. So it's equal to 1,624 sorry, I forgot to write, sorry, I got this bit wrong here. 1,600, it's quite a long number, so 162411487. Okay, now if you're doing A-level physics, they don't like you to write like this, so essentially you would have 1.624 multiply in standard form, multiply by 10 to the power of 9. That's Newton per meter square. And power of 9 is giga, so it's 1.624 gigapascal. Okay, so they will accept if you write Newton per meter square, but A-level physics, I think you might not get away with that, so you have to write gigapascal. And that is the tau answer. So to finish this off, G is therefore equal to the 1.624 times 10 to the power of 9 divided by the strain, which we got is 0.075. Oh, yeah, it is right. And so again, because that's unitless and that's in Pascal, so the answer will still be Pascal. Okay, so it's 21.65 gigapascal. Okay, and that's it. That's your 9 marks. Thank you for watching.